Alrighty. Oh, wow. This mic must work. Everybody stop talking. Excellent. Hi, I'm Jim Weirich. I'm the chief scientist of EDGECASE, and I'm here to talk about Connascence. Now, I have to say that word very carefully because I talked about Connascence before, and I very carefully pronounced it Connascence with two N's in it the very first time I said it during my talk, and then mispronounced it for the rest of the talk. So let's just all kind of practice that together. Connascence. 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 One more time. Connascence. Okay, so if you get anything out of this talk, you'll be able to go away from this talk and impress all your coworkers with a word that they have no idea what it means. Okay, how many people here have some inkling of what connascence is? Okay. Okay, some of you might have seen my other talk. There'll be a lot of repeat stuff in here, but we've also got some new stuff in here, so it'll be a little bit of
described it in the program also.
Someone read the abstract. Imagine that. Well, okay, so let's not talk about connascence right away. First, I want to tell a story about some twins. There were once two twins who were, well, twins. They were born on the same day. They were the exact same age. And one of the twins decided to take a rocket ship ride. And he climbed in his rocket ship, and he took off. And this was an amazing spaceship. It traveled at 80% of the speed of light. We call that 0.8 c, c being the speed of light. And he traveled that way for what seemed to the brother left on Earth for 5 years. He then turned around the spaceship and traveled back again, back to Earth at 0.8 c, or 80% of the speed of light, and spent another 5 years returning the spaceship. Now, amazing thing happened. When he returned to Earth, he discovered that there's this thing called the Lorentz contraction, or the Lorentz time dilation. And actually, the time that he spent on the spaceship was not quite what he expected. And there's a formula here. Now, if you were at Chad's keynote talk yesterday, he had all kinds of formulas on the screen. This one's really simple. There's only one variable in here called v, because c is a constant. That's the speed of light, and that'll be 1, because we're measuring things in terms of the speed of light. So v will be 0.8, and we can just plug the numbers in and see what this works out to. So let's square all those things up. That's 1 minus 0.64, gives us 0.36. Take the square root of that, and we get 6. Multiply that times the 10 years that the brother spent in the spaceship, and we found out that for him, it only seemed that 6 years passed. Now, what's amazing is that in 10 years, his other brother grew a full beard. This is true. Well, actually, I don't know if the twins actually use a spaceship or not, but time dilation is a true fact of special relativity. And even though they were twins to begin with, they had lived the same amount of time, the objective time spent for the twin on the spaceship was actually 4 years less than the time observed by the guy left back on Earth. And this has been shown experimentally with cosmic particles that penetrate the Earth's atmosphere from the sun, and they decay at a particular rate. And the speed at which they move and the speed at which they decay means that very few will reach the surface of the Earth. But we find that they are so fast, they are traveling so close to the speed of light, that the average half-life of these particles are actually much, much, much longer than what they should be if they were standing still. So time dilation is a true fact of special relativity, and it's shown by this simple formula. There's all kinds of cool things about special relativity that I'd love to talk to you about. But the reason I wanted to talk about the twins is because they were two things that were born together, and we expect them to change together. And that's essentially what connascence is. Oh, by the way, if you want to know more about special relativity, there's a marvelous site called Minute Physics. Every week they put out a 1-minute video that talks about different aspects of physics, and they just recently did a wonderful 1-minute explanation of special relativity, one of the best 1-minute descriptions I've ever seen of it. So check that out if you like physics at all. But so, what is connascence then? I got connascence from a book called What Every Programmer Should Know About Object-Oriented Design. This is an awesome book with an awesome title. Little pretentious maybe, but that's okay. The book is written in 3 parts. The first part just talks about basic OO stuff that probably most of you know already, if you've been doing any object-oriented design at all. The second part of the book develops a graphing notation, graphical object notation that you can use to talk about object systems that nobody uses. So forget that part. However, the third part of the book talks about design principles in object-oriented design and introduces the concept of Kinesins. Now, I've talked to Mueller Page Jones, or we have emailed back and forth, and he confesses he tried different words. He test marketed different words. He tried interdependencies, or he tried the word coupling, and none of the words tended to convey exactly what his meaning was, because when we hear the word coupling, we automatically think we know what coupling means. But since we're introducing a new word, Kinesins, which is a real word, we get to define what Kinesins means in the software world. Okay, so what does it mean? Kinesins itself means it's talking about the common birth of 2 or more things at the same time and the production of 2 things that tend to grow together, that tend to say the same. So Kinesins in software are those things that need to change together. If I change this item over here in module A, and because I've changed this thing in module A, this thing over here in module B needs to change, well, that's Kinesins between those 2 modules. It's another word for coupling, but we're going to give it very particular meaning here. Actually, there's lots of different kinds of Kinesins. Mueller Page Jones talks about 9 of them. I'm not convinced 9 is a complete list, and we'll talk a little bit about that later. And so we're going to hit all 9 of these. Some of these we're going to hit really fast. We're also going to talk about some principles, and we'll also briefly mention something called contrasence, another good word. But I'm going to skip name and position. I'm going to go over them really fast because I think most people have a good understanding about name and position, and I've talked a lot about them in the past. I'm going to concentrate on the remaining 7 and then these 3 principles in this particular talk. So let's cover name and position Kinesins just very quickly here. So what is name Kinesins? Suppose you have 2 modules where in one, Ruby developers in here? Raise your hand. Java developers? Okay, C#? A little bit. Okay, Kinesins applies to everything. I'm a Ruby developer, so a lot of my examples will be in Ruby, but this stuff, for the most part, applies across languages. We have a definition of a method here called foo, and then we call foo over here. This is Kinesins of name, because if I decide to change the name of my method foo, I obviously have to change the name of every place where foo is called. So there is a connection, there's a coupling between the definition and the call site, actually between the definition and all the call sites, and this is just simply Kinesins of name. Simple, right? Straightforward. I'm not going to spend much more time on that. But we'll be using Kinesins of name a lot in the rest of the talk. Kinesins of name occurs whenever 2 components must agree on the same name. Now there's another type of Kinesins called position. And Kinesins of position is something like this. Suppose we have a calling sequence, a method called bar. And we pass it 3 items, name, title, and address. And the 3 things are declared at the definition point, and they're also declared down here at the calling point. And notice that the name has to be in the same position of the calling sequence as the name variable where it's defined, and the title has to be there, and the address has to be there. So if I were to change the order of my parameters in this list, I would have to change the order of every parameter, or every place that was called, to match the changing of order. This is called Kinesins of position. So Kinesins of position occurs when 2 components must be adjacent or appear in a particular order. Now, calling sequence is an obvious example of kinesins of position. How about you guys? Any examples off the top of your head? An SQL query, yes, because you specify the columns in the query and the data will come back arranged in the column order that you specified.
Later in the code, we might add something.
And interesting, that they might come back that way, but a lot of times, depending on your language interface, you'll get them back in a hash, which means that you have named columns. So in that case, that's kinesins of name. In fact, let's look at this. In Ruby, you can have, in essence, keyword arguments passed in. So if I were to change this bar here with 3 explicit arguments in this order into a type of routine that took named arguments and passed in like this, I have converted kinesins of position to kinesins of name. You'll see that a lot. At Rails, if there's got any Rails developers in here, you'll see a lot of Rails routines use named keywords where they have a lot of parameters being passed in, especially if you have optional parameters, because you can leave them off. So when I think there's something we call degree to kinesins. You can have a strong coupling in name because you're depending on a lot of names or a lot of positions. I'm okay with 1 or 2 parameters in a method. I'm okay with 3. When I get up to 4, I begin to get uncomfortable. Your threshold might be higher or lower than mine. But around 4, I start thinking, maybe I should convert this to a keyword argument and convert a high degree of position kinesins to a smaller degree of named kinesins. Okay, so it's a position kinesins and a name kinesins. Okay, let's talk about the interesting ones. Why is kinesins important? Change is expensive. You want to, it's good software practice to reduce the coupling between your modules. And kinesins is a way of talking about coupling in a particular way. And that's what we're trying to get at here. Let's define exactly what coupling means. And here we have something called kinesins of meaning. What do you think when you see code like this? I'm sorry? Static? Sad. Oh, you feel sad. Why do you feel sad?
Better ways to represent the absence of the value.
Yeah, there is a particular value here, the 999999999 Social Security number, which is used to represent possibly, essentially that there is no SSN. It is a special value. And this value has special meaning to the program. This means that everywhere you use a Social Security number, that you should probably be checking it for this particular value to see if it's a special one-off value. This is kinesins of meaning, where data values have particular meanings that must be interpreted consistently across the program. Now we can fix this a little bit by maybe putting in a named constant here, but we really haven't changed it. We've added some named kinesins here, which is a good thing. I think migrating towards named kinesins in general is good, but it's still kinesins of meaning because we have a particular data value that has to be interpreted consistently. I ran across code like this in one of the projects I worked on recently. Now, obviously, this is a list of carriers that they're going to be displaying to the user, and some numeric encoding scheme here, and I have no idea why it starts at 10 rather than 0 or 1. But the fact I see Wi-Fi down in here, and this is actually a little Ruby trick, that this is an expression that returns 15. So it's as if I wrote 15 here, but as it also defines the constant Wi-Fi to be 15. So I can refer to Wi-Fi later. So I've essentially namified that constant. So So we got kinesins of name going on here, but it's also kinesins of meaning, because that means I have to interpret this 15 represented by the constant Wi-Fi in particular ways. And you know there's code like this somewhere in your system. And actually, why Wi-Fi is a carrier is an interesting choice. This is for code that sends a text message when you sign up. But if your device is not on your iPhone, or probably this is for an iPad. If your iPad isn't on a carrier but is on Wi-Fi only, well, you can't send a text message. So there's a different way of doing it. So yeah, that is a special value. Other, I think, is just for carriers that we don't know about, that we don't explicitly code for. And then we've got this UK and Canada stuff in there, which, you know, there's some code in there that says, if you're in Canada, well, then do this. So you know that's in there somewhere. So yeah, lots of kinesins of meaning going on here, and that bothers me a lot. What would be a better way to do this? Symbols, possibly. You still got the kinesins, you still have to interpret the symbols correctly. One way is maybe convert this, instead of a simple association here, maybe convert this to some kind of structure that says, okay, is this a carrier or not, and have it used consistently. Then it's just data. Then it's a field that describes that piece of data rather than special numbers that we're doing testing on. What if we had something other that was not a carrier but wasn't Wi-Fi either? Well, then we have to go back to this code and say, is it Wi-Fi or something else? If we have a field that says, is this a carrier we can send a text message to and make that self-reflective, then we can put that test here and we can change it in one place. That's localizing the change. So gathering this up as data rather than special values, I think, would be one way I would go with this code. All right. So kinesins of meaning occurs whenever two components must agree on the interpretation of data. Okay, for the Rubyists in here, what does this method do? Who knows? Go ahead.
Displays all of the instance methods available to fix them.
Okay, pretty obvious. What do these methods do? It's kind of those, I hate those ones, yeah. One of these is exactly like the first one, displays all the methods available for the fixed num class. The other one displays all the methods defined explicitly in the fixed num, but not in the ancestors of fixed num. Which one is which? Okay, first one's all the way up. How do you remember that? Because please tell me. You just looked it up, okay. I did too, yeah. Since I just looked it up for this talk, I know. But I forget it every single time. This is kinesins of meaning. We have assigned a particular meaning to the values true and false that is not evident from their usage right here. Now, here's another example. This is Rails, okay? And we have finder methods, and you can say colon all or colon first. Now here we're using symbols. Someone suggested switching to symbols. So here we are actually using symbols rather than true or false, thanks goodness. I know which one of these which one of these finds all of them, and which one finds the first one. But you know what's really unusual about these methods? This method, it's one method called find. In one case, it returns a collection of objects, and in the other case, it returns a single object. Oh, that just hurt my head. Now, it turns out this doesn't bother you 99% of the time, because if you call find, you pass in either all or first. But what if that was a variable? Suppose you wrote locate, and you passed in all or first here. You call find, it passes in the right thing. Now you want to know, did it succeed or not? How can I tell? Well, if it was a single object, if it fails, it returns nil. If it's a collection and it doesn't find anything, it'll return an empty collection. I have no idea which condition to test for because I can't tell from this code which thing I'm returning. This is a special case of kinesins of meaning. And in the old days, we called this control coupling. Control coupling is passing in data to a method or a function that controls its internal algorithm in some very explicit way. Here we're telling find to find all, find a collection, or find a single object. And we're telling it by passing in a flag. Control coupling occurs when one of the components passes a piece of information that is intended to control the internal logic of another. As far as coupling goes, control coupling is right there in the middle. It's not entirely evil, but it's not all the way good either. So I'm always sensitive to when I see cases of control coupling going on. And I feel that a lot of developers out there don't care about control coupling at all. And I would like to see that change. Warning signs for control couplings. Here's a couple things that you can use to tell if you're in danger of control coupling. If you've got or in the description of your function, well, it returns an object or a collection. It returns the methods in the class or the class hierarchy. I like this last one. It either reads or writes to the disk. And you laugh at that. But I remember way back in the day, I was working on a fourth system that had a low-level disk I/O function. It was called I/O. And it did I/O. It would either read or write. It would read into the buffer or write from the buffer, depending on whether you passed it a 0 or a 1. Ooh, control coupling there. Yeah, so it happens. Other warning signs. You're passing in data that has no intrinsic meaning to the problem. Symbols are, now, not all uses of symbols are like this, but symbols have the potential of being control data. So examine your uses of symbols to see if you're doing control coupling. First versus all is an example of control coupling. True, false. Again, all uses of true, false are not control coupling. Returning true or false from valid question mark is that's data. It tells you something. It's intrinsic to the problem definition. True or false, whether do you get all the methods or just part of the methods, that's control coupling. Nil is an interesting one, because a lot of times nil just means no object. But sometimes nil means something special. I don't think this is the case anymore, because I couldn't find it in the documentation, but I'm 90% sure that in the old days in Rails, if you returned nil from a filter, it would tell it not to continue processing a controller action. I don't think that's true anymore. I think it depends on whether you rendered or not in your filter, but that's fairly common, returning a value to tell it, to process more or not. That's actually control coupling in reverse. We're using the return value to do control coupling. So nil, I've seen interfaces, and I couldn't find one for this talk, but I've seen interfaces that make a distinction between nil and false. Yes, yeah, someone said, yeah. I can't remember what they were. I tried to purge those from my brain, but yes, if I return nil, then this means that. But if I return false, it means something else. And my goodness, what does that mean? You know, that's definitely control coupling there. So be aware of those signs. If your code is written like this, if you pass in a flag and the flag is just used to either do this or that or some kind of case statement, that's probably control coupling. Take a good hard look at that. Okay. I've used up almost all my time, and I only talked about kinesins of meaning so far. Let's talk about kinesins of algorithm. I was writing a wiki program, because everybody needs to write at least one or two wiki programs in their life. Actually, as a test bed for some ideas that I wanted to try out in this talk. One of the things that came apparent is that on the page object, we wanted to, in a wiki page, there has to be a particular format for the name of the page, generally capital, camel-cased letters beginning with a capital. So it has to match this particular pattern, so I use validates format up here. But notice that here, when I actually render the text, I want to go and find all the wiki names on a page and replace them with an actual link, a URL link. And I do that by using not an identical, but a very similar regular expression. This is kinesins of algorithm, where two pieces of your code base have to agree on how to process things, or things become broken. Now, an obvious fix for this is to go up here and create some constants so we have the regular expression once, we reuse it here in this expression, and then we can use the regular expression here and here, and it's only defined once. So we've dried up this code, and I won't say eliminated, still kinesins of algorithm. These two pieces still need to agree, but we've kind of, again, namified it. We've introduced kinesins of name to help control the algorithmic kinesins going on here. Kinesins of algorithm occurs when two components must agree on a particular algorithm. Any other examples of kinesins of algorithm?
Like a client and server agreeing on a protocol?
Yes, yes. Or an encryption scheme, or a compression scheme. If I compress using gzip over here and try to uncompress it using something else, it's not going to work. We have to agree on the algorithm we used to compress. And this is particularly interesting because it could be that this is an entirely different program written in a different language than this one over here. So kinesins of algorithm can't be trivially fixed by creating a method or creating a library and using it in both places. You have to perhaps actually re-implement the algorithm in different languages. So yeah, that happens a lot in communication protocols. Checksumming. If there's a particular algorithm for making sure that the numbers in a credit card are correct. I forget the name of that algorithm right now. I used to know it, but you essentially sum up the digits and mod at 10 and subtract it from this, and then that's the last digit of the credit card. Well, that's a kinesins of algorithm that everybody has to agree to use that particular algorithm when checking on credit cards. Here's another example. In Rails, the heart of Rails is the router that takes a URL and figures out what controller and action need to be called based upon that URL. Now, conversely, when we display a view in Rails, we need to generate links that will eventually resolve to controllers and actions. So there is some kind of connection between the URL coming in and the URLs that we need to generate. I don't remember, if you know in the old days, do you remember when we had to do this kind of thing in URLs? Oh, that's ugly. And everybody complained about it, and it wasn't good standard practice. And so eventually they changed it to this. They changed the algorithm for generating URLs. That meant every place that generated the URL had to be fixed to generate the new version of the URL. It was kinesins of algorithm between the router and the code generating the URLs. Now, if you were smart, we're using named URLs, named paths. And this one handles all the details on how to generate a URL that goes to a new pages page. And then, again, this is introducing kinesins of name now. We're depending upon the name of a method and using a common library to control kinesins of algorithm, reducing kinesins of algorithm to kinesins of name. We'll see this theme over and over and over again. One of the things that you can do in designing a program is strive to reduce the kinesins by reducing the degree of it. I believe that the different kinds of kinases are in some kind of hierarchy. I think name is probably one of the better ones. I think that position is not as good as name. I think some of the others are kind of in between and under them. I wish I could give you an exact numerical value for each of them, but I can't right now. But use your gut feeling and look to reduce the kinds of kinesins that you're using. In general, that means driving towards named kinesins quite a bit. Kinesins of type. This is a really, really interesting topic that we're not going to talk about. Actually, I wasn't going to talk about it at all, but right before I was sitting in the break room and I said, yeah, I do want to say something about this, but I'm going to delay it until we've talked about some of the other things. Now, of the 4 kinds of kinesins we talked about so far, name and position, meaning, algorithm, and I guess type, so 5 kinds. These are all static kinesins. You can go and you can examine your source code and say, oh yeah, we use the same name here, or look, they're using the same algorithm. You can visually inspect your code base and say, yes, there is kinesins between these 2 parts because I can see it in the code. The remaining 4 kinds of kinesins that we'll talk about next are a little trickier in that they have to do with the runtime of your program. You may not be able to detect these kinds of kinesins based upon just an examination of the source code. You might actually have to run the system and see how the pieces interact with each other. Okay, so keep that in mind. Kinesins of value. This is an interesting one. I do a test-driven design talk where I have people write up test cases for triangles. I say, you're writing a function that takes 3 integer inputs, 3 numeric inputs, and you're supposed to analyze these 3 numeric inputs and say whether the triangle formed by the lengths of these sides is an equilateral, an isosceles, or a scalene triangle. And then write a set of test cases that list the 3 inputs and the expected outcome, equilateral, scalene, or isosceles. What is really interesting is that what people forget, there are values that cannot be triangles, sets of 3 values that cannot be a triangle, okay? So here's A, B, and C. Okay, those are all good values there. So suppose we flatten the triangle a little bit. Okay, that's still a triangle, although it's pretty flat. What is the relationship between A, B, and C that expresses a valid triangle? Well, the next slide will tell us that, oh, if A and B are too short, in fact, if the sum of A and B is not greater than C, you do not have a valid triangle. So this condition right here needs to be true in order for those sides to be a valid triangle. This is kinesins of value. And here, we've captured that information here in a function that it takes A, B, and C, sorts them into X, Y, Z. So X and Y are the short ends, Z is the long one, and it just makes sure that the triangle is valid. So there's a simple way of testing for that particular kind of kinesins. Kinesins of value occurs when the values of 2 components are related. So this is a runtime thing. If I change the value of this variable, what happens to this variable over here? Do they change? And there can be really, really interesting relationships between these. The triangle one is an obvious one. Other simple examples that come to mind is maybe graphical programs where you have maybe the sides, the positions of the points of a rectangle. You can't do this. You can't put the left side on the right side, things like that. So you have to be aware of things like that. Any kind of constraint programming you're doing is interesting. Possibility of value kinesins there. There's possibility of value kinesins even in regular code that you write. Suppose that you're iterating through some kind of loop and you're keeping track of 2 different things, and in order for the loop to terminate, those values have to, as one decreases, the other increases or something. Those are related by a kinesins value. To keep the loop invariant constant, you have to worry about those values are related correctly. These are all possibility for value kinesins. The nice thing about value kinesins is it generally is not widespread. It's very localized. If these 2 values need to be related, generally they're in the same module or the same class and the same object. When you have values that are widely spread across the system that need to be kept in sync, that's where you have problems with kinesins of value. You can guess what this one is. I've used this example before. I love this example. Suppose you have a simple account object, and you initialize it to a balance of 0, and it has a single method called deposit that increments the balance by a particular amount. And then you go and you run this in a code that looks like this. How many people here do threaded programming regularly? Raise your hands. Oh, you brave souls. What's wrong with this code right here? We're sharing state and we're modifying state, and we're not doing anything to prevent two threads from modifying that value at the same time. If I were to run this code, I create 10 different threads, and then each thread 1,000 times increments the deposit, deposits $1. So by the end of this program, the balance should be 10,000. Every single time, it should be 10,000. So let's run it a bunch of times. Yeah, that's called a race condition. A race condition is nothing more than connascence of timing, where the timing of execution affects the outcome of your program. That's actually the definition of a race condition. Race conditions are an example of connascence of timing. There are other things. You could have connascence of timing in things that are not necessarily tied to multi-threaded things. Perhaps, especially if you're dealing with external things. I worked on a project where we had hardware physical devices. And when you talk to hardware, that's funny sometimes because they don't respond in the way that you think they do. They're not pure software. They will be slow or they're busy doing something else. So we have timeouts in our code. And if the timing of things don't work out exactly right, we could get a bad value back, a timeout on the thing. That's connascence of timing, where the timing of execution of your entire system affects the outcome, is connascence of timing. That is a problem in real-time systems. It's a problem when you're talking with hardware. It's a problem when you're talking about threaded things. Other than that, I don't think you're going to run into it too much. But it's an important one to know, and it's important because people think, oh, threaded programming is easy. But it's not. Fixing this problem here is actually a much deeper issue than what you might suspect. But that's an entirely different talk that we're not going to do right now. Okay, connascence of timing. Race conditions and timeouts. This is an interesting example here, kind of related to the timing example, but a little bit different. I wrote a script here recently. When I do traveling, I get receipts, I gather them up, I scan them in, I plop them in a directory, and then I run a script that goes and copies each of my scanned receipts and files them away on my local hard disk, so I have a copy, and then also files them away in a Dropbox for EdgeCase, so they can go pick it up and look at it. So I get a copy, and EdgeCase gets a copy, and so I know what they've got, and it's all scripted so it works automatically. So for each receipt that we find, we copy it to the EdgeCase Dropbox, we copy it to my local directory, and then I remove it from that temporary directory where it was sitting. Now these are 3 lines. It does not matter whether I submit to EdgeCase first or file it locally first. Makes no difference. However, if I were to purge the receipt first, it would break the thing. There is connascence between these 2 lines. Actually, between the first and the third line and between the second and third line. And this is connascence of execution, where the ordering of the execution of your code is important. Now, we as developers deal with this all the time in imperative languages, and we're used to this. The interesting thing is that if you were working in a purely functional language, you don't have any issues of Kinesins of execution, because everything is returned values, and you don't actually change anything. So I'm not quite sure how I would write a script in a functional language that would do that, but the whole expression evaluation thing solves this entire problem for functional languages. But in imperative languages, we still need to do this. Here's an example. I mentioned that I worked on a project that talked to hardware devices. And this particular device sent us messages every so often. And a lot of the time, the messages were of this, first message was, okay, start a list. Here's the first item of the list. Here's the second item of the list. And here's the end of the list. So it was very, very important that these messages be processed in the order that they were sent. Now, the system was architected like this. Now, I'm leaving off a lot of the details, but the device essentially sent the messages and they got placed in the queue, 1, 2, and 3. And we had a worker here that pulled items off of the queue, 1, processed it, 2, processed it, 3, processed it, and then we go on. And this worked great. It ran on my local box, no problem. I pushed it up to our QA box, no problem whatsoever. We moved it to our staging boxes. Notice I said boxes. Staging environment was a little bit different than our local development, our QA box, because they had multiple workers. Some of you are smiling. You see what's coming on. So worker number 1 would grab the first message and start processing it. Worker number 2 would grab the second message and start processing it. And for some reason, worker 2 was a little bit faster than worker 1. And the second message would be sent to the database before the first message. And I'm getting a list item and I don't have a start of list yet. And our software would blow up and complain. Connascence of execution. These items must be executed in a particular order for the software to be correct. Now, we solved this problem by creating what we called well-ordered queues, that once a worker started processing the queue for a particular device, and we had thousands of these devices out there, but once it started processing a device, it would empty the queue, and the other workers were barred from talking to that particular device. But they can go and work on the queues of other devices. That was perfectly fine. So they were all still doing work, but I guarantee that for a given device, all the execution was well ordered. That was a good several days of debugging and coming up with a solution on that one. So Connascence of execution, very important. Connascence of execution occurs when the order of execution of 2 components is important. This is an interesting one. Let's go back to our wiki application. The Wiki Rails app was a multi-wiki site. In other words, I could have multiple wikis, and every wiki would have its own set of pages independently of the other. So you could support maybe several different kinds of wikis, all off of one Rails application instance running. Here is the page. It belongs to a particular wiki, and every wiki kept track of what the home page was. So when you initially go into a wiki, it takes you to the home page, and that home page could be different for every single wiki. So the wiki object saved the title of the home page. So what happens when I ran this particular test? Let's walk through this one, okay? I create a wiki with this name, and its home page is the old home page. I create a set of pages. This page is the new home page title right here. And then, okay, so so this is the setup. When I call make home page, and this is make home page right here, we just save the title into home, and then we save the wiki. So that should save its own title. The new page should save its title in the wiki. And then we assert that wiki.home should equal the new home page. Fairly straightforward, right? Okay? When I run this, whoops, it didn't work. Anyone know what happened here? Did I reload the wiki object? That's really interesting because it's all in memory. Why didn't it just find the right one? I did write to the database. What happens is there are actually two wiki objects involved here. And here, this was the model I had in my head. I had a single wiki object with an ID of 1, and it had multiple pages, and the pages pointed back to the wiki. However, that wasn't what the real situation was under the covers. Under the covers, we had this. We had the original wiki I created, and we had the pages, and then when I referenced the wiki from a page object, it didn't go back to the in-memory one that it had. It hit the database and reloaded the data into a new in-memory object that represented the same wiki object in the database, but now I got two in-memory copies of it. Okay? Rails does this because it does not use an identity map. Some ORMs will guarantee that whenever you grab an object from the database, you always get the same object back, at least within a transaction. Rails doesn't do that. You could have multiple copies of your objects running around in memory. And so I loaded this one up. I called set page on this one. So this had the new title. I saved this one to the database, so it had the new title in it. But then I went back in the test, I grabbed my original one and said, do you have the new page? And it says, no, I've still got the original because it's an in-memory copy that was out of sync with the database.
New option to enable it. I think you can hit option to turn on a identity map that's not state.
I just talked to Yehuda right before this talk, and I asked him about that because I knew someone would bring that up. He said that he wrote an identity map for Rails. He put it in, and it was about 90% there, and they decided to take it out because they decided that 90% of an working identity map wasn't good enough. So they took it out. I don't know if it will come back in or not, but right now there's all kinds of implementation issues with identity maps, and you got to do it right. It's a tricky thing. And truthfully, a lot of developers after 4 or 5 years of Rails are expecting this behavior anyways, and an identity map will probably screw them up because they're thinking it's not working that way. So just be aware, this has caught me on multiple projects before. So this is Kinesins of identity. It happens when two components must refer to the same object. Okay. Questions so far? Yeah?
In that test example, what would you do to make the test pass?
Okay, good question. What would I do in this test example to make it pass? It's a couple things. In my test, I could say page.wiki.home, so I get to the wiki object that page was actually updating. I could say reload wiki here, and that would cause the out-of-date in-memory copy to go out to the database and refresh itself. I could mock out everything to the database and just assert that we've saved it. There's lots of approaches here that could have been used. Probably for this one, I would either reload or just go page.wiki.home right here and just know that, hey, I'm dealing with getting to the same object through different paths, through different associations are going to yield different in-memory objects, and just be aware of that. Yeah, good question. Okay, anyone else? Okay, let's see what we're doing on time. We got 10 minutes yet, good. Let's talk about Kinesins of type. I passed on this one because I think Kinesins of type is an interesting type of Kinesins. Not to use type twice there. Different, interesting kind of Kinesins. And I'm not quite sure I understand all the implications of Kinesins of type yet. What is a type? Anyone? Duck type? Okay. What's the classical definition of a type? definition of an object. Okay, a lot of times we associate class with type. That's not quite correct in type theory. They had a bunch of talks yesterday on types. I wished I could have gone to them. But essentially, the classical definition of type is it's a set of data values and a set of operations on those data values. For example, integer is a type. You have the values 1, 2, 3, 4 on up, or negative 1, 2, 3, 4 on down, plus 0. You have operations. You can add integers. You can multiply integers. You can subtract integers. You can divide integers, and that's an interesting operation because the divide operation between integers may not yield an integer, okay, but it's still an operation of its type. So things of value, things that you can do on those values. My favorite example of a type is a stack example, right, because it's simple to understand. A stack is essentially a collection of objects ordered in a particular way, and it has a handful of operations. Here I just list out push, pop, and a query called empty. It'll tell you whether the stack is empty or not. How do we analyze the kinesins of a type? What if I had a program that used a stack? Well, there's kinesins of name because we have to agree on the names of the type. Okay, stack, I'm using a stack here, I'm using a stack. At least in manifestly typed languages, like Java, I have to actually declare, the types. In Ruby, that's a little iffy because we don't have to actually name the type, we just have to use it. So the name of the type may or may not be part of the kinesins depending upon what language you're using. Well, what else goes into this? Well, if I'm going to use a stack, I have to assume there's going to be a push, a pop, and an empty operation on that. And that's kinesins of name because I've named those operations. And you can see here, it's hard to see on the thing, but there's yellow there on stack, push, pop, and empty. That's indicating some kind of name kinesins. There's a parameter list for each of these things, and stack is kind of boring because it only has one parameter right here. But if there were multiple parameters, there'd certainly be some kind of kinesins of position here, and certainly we have to depend upon exactly what arguments are given to those operations. So there's some kind of connection there, possibly position, possibly something else. And then for each of these things, I've got this purple dot over here for a type of kinesins I don't know what to call. What happens when I push an item onto the stack? Well, depends on what kind of stack, okay? What would you expect to happen?
It's on the top.
Yeah, you push an item, it goes onto the stack, and if you pop it immediately, it's what comes off the stack. Okay, there's a certain semantic associated with a stack that you expect to work. And that semantic is encoded in your client code that uses it. If I push an item onto the stack and then pop it, and I don't get that item back, that stack is broken for me. So there's some kind of connection there. If I change the semantics of push, I will probably have to change the way I write my client code. Connaissance of algorithm? Quite possibly, quite possibly. In fact, or semantics, or I'm thinking there might be a new kind of connaissance, and I'm trying to think maybe connaissance of semantics or maybe connaissance of contract. I like to think of things in terms of contracts, preconditions and postconditions.
Why not just connaissance of meaning? The operation push has a specific meaning to your user.
Well, connaissance of meaning is that's when you interpret a data value in a particular way. So we're already using connaissance of meaning to mean something a little bit different than this. Connaissance of expectation, that's an interesting one. Yeah, so anyways, but we can agree there's something going on here. Algorithm might be a good term for it. Contract might be a good term for it. Something's going on there that's in addition to just more than just the name and just the item. And I think that's important. A lot of times you talk to a Java developer and they'll say, well, our interface defines our contract. No, it doesn't. The interface defines the name and the argument list, which is essentially kinesis of name, kinesis of position, but it says nothing about the semantics. And there is something going on here that we have expectations when we call this. And there is some kind of kinesins based upon those expectations. So, kinesins of type, to summarize this, is kind of a summary of all of this. You have the kinesins of the name of the type plus the number of methods times the name of the method plus the kinesins of the arguments plus the kinesins involved in the semantics. And so kinesins of type is a very complex type of thing. Yeah, you want to say something, I can tell.
I was thinking that all the other kinesins were as primitive as possible. This one's got a meta kinesins, and why not just say that it's all those separate kinesins and not leave it over
And that's a good question, and it might possibly be that. Mueller Page Jones in his book doesn't get into that. And I think this is an area that I would love to see someone do some study in this area and see if they can tie that down. And it might be me or it might be one of you if you get time to do it. That would be awesome. But I think it would be well worth thinking about that. But type kinesins is actually very, very important. And it kills us all the time. Let me give you an example. This is a way back in my Java days. I was writing a piece of code that used a prepared statement of some type, which is an interface. And I wanted just to test it. And I wanted to create a test double that mimicked the prepared statement. We'll call it a faux prepared statement. Has anyone ever tried to implement the prepared statement interface in Java? Well, this is what I wanted to write, something like this. I wanted to be able to set the integer and then call execute query and get some kind of result set back and just kind of stub this out here and return some hard-coded values maybe. And this is the code I wanted to write. This is the code I had to write. The surface area, that's a good term, the surface area of the prepared statement interface is huge. There's almost 100 different methods in there. And the fact that I was tied to, the fact that I was using the interface meant that I had to implement all the methods in the interface, whether I used them in my test code or not. They had to be implemented. So most of them were just stubbed out and returned zeros or null or whatever was appropriate. That was a mess. It'd be so much easier in Ruby, you know. That was my opinion back then when I was actually doing this. And yes, it would be easier in Ruby. This is what you would write in Ruby. And notice this is the same problem, but kinesis of type in Ruby has a different set of properties. First of all, in the Java version, we're depending upon an interface, so the interface defines the type. And that's convenient because there's one place to go and you know exactly what it is, but also inconvenient because in this case, a prepared statement interface is huge and unwieldy and difficult to implement, to fake out. Now, there's tools these days, EasyMock and these other things could have probably done that a lot easier than I did, but I was doing this way back before those tools were available. The Ruby version, however, throws out the interface. The kinesis of type is between the client and the faux prepared statement. There is no interface there. So instead of having two paths of kinesis of type, I only have one. And the really interesting thing is the definition of the type resides in the client. What the client uses defines what the type of the thing I have to provide it for testing. So if I'm only calling set integer and execute query in this, that is the type that I have to provide for testing. And this is really interesting, but I don't know what to do with this. Right now it's just an observation, but I'm thinking kinesis of type is a really ripe area for investigation. I would love to see some people do some deeper studies on that. So kinesis of type occurs whenever two components must agree on the type. In manifestly typed languages, you have to explicitly name the type and you have exactly what the operations are. In a dynamically typed language, the type is a little more fluid and a little less defined, and I think the kinesins is weaker in that case, but that doesn't mean it doesn't exist altogether.
You can probably still run into problems with strongly typed languages. For example, in Java, if you define a method that takes a particular interface, then inside that method, you say if it's an instance of such and such child, then do
Yeah, explicit testing for types. You can actually do that in Ruby. And in Ruby, we like to call it, there's duck typing, where you just take an object and you just call the methods you want on it. And if it acts like a duck, it's a duck, and we call that duck typing. There's also a style in Ruby where you pass an object in and you explicitly check, is it a string? Is it an array? Is it this thing? We call that chicken typing. Because we're just a little bit afraid it might not be what we want. Yeah, I'm not a big fan of chicken typing, either in Java or in Ruby. Okay, one last thing. How are we doing on time? We are a minute over, but I'm the last guy talking, so you've got to stay here till I'm done. Just real quick, I don't want to talk long about connascence, but I think this is also an area that could really do some research. People rag on inheritance all the time. The problem with inheritance is that things in the child interfere with things in the parent. If I define a foo down here and there's a foo in the parent, they override each other. The child overrides the parent. This may be intentional or may be unintentional, and that's the problem. If I change the parent, I possibly break the child. Likewise, instance variables the same. So people say, don't use inheritance, use modules instead. Yeah, same problem. Modules don't solve this particular problem. Some people think, well, I think there's a movement called, I think it's called DCI, that says, well, let's mix in the modules on the fly. Well, you no longer have different modules interfering with each other, but you still have the parent-child relationship. And that's called contranascence, when two components must agree on different names. And I think contranascence is kind of the problem with the whole inheritance thing. And I think that would be an interesting thing to look at. So anyways, namespaces, delegation versus inheritance are ways to deal with contranascence. And actions. Reduce the degree of your kinesins in your code. Increase locality. And things that need to change together, put them in the same module. Bring them closer together so they can change together more easily. And don't repeat yourself as kind of an application of increasing locality. Single responsibility principle also moves in that direction. So I think these things are kind of based upon the locality idea in Kinesins. And also, this is a new one I've just recently added. Depend upon things that are stable, things that don't change. Kinesins, if I have strong kinesins with something that's changing all the time, that's a problem. But if I have strong kinesins with something that doesn't change, I'm fairly certain that these string methods in Ruby are fairly stable. No, wait, they just changed that between 1.8 and 1.9. Forget all that. No, but system things that are fairly stable, those are the kinds of things where kinesins is more acceptable than on things that are very volatile. So prefer things that are stable. Future, I think we should be researching the contranascence. I think kinesins of type is also an interesting thing to look at. I'd love to hear your thoughts on this, and thank you very much. I'm Jim Weirich with EdgeCase. Have a good day.